Welcome back. So what we're going to do now is we're going to dig into the details of this idea of positional information. That's going to allow us to talk about reaction-diffusion equations, and it should be fun, and it conveys a lot of sort of intellectual power, as you'll see. So I want to just remind you of what the concept is here. The concept is that in the early fruit fly embryo, there are a succession of cascades of gene expression, and one of the most celebrated is the so-called bicoid protein, which you see the morphogen of, or the gradient of here. And what I want to do is I want to try to talk you through the underlying mechanistic aspects of how this gradient is set up, or at least a hypothesis for how the gradient is set up. That's going to be the subject of this current vignette. And then the next vignette will exploit the existence of this exponential profile in order to think about the so-called French flag model, which is a really fun predictive insight into positional information indeed in the fly embryo by changing the height, if you like, of this exponential gradient. So what we're going to do is we're going to try to write down a continuum theory of the concentration profile in the embryo. And the thing I want to point out is that the mother deposits in the anterior end some mRNA. That mRNA is translated, and the result is proteins. So I have some protein. This is the bicoid protein. And what it does is it undergoes a random walk, and it's degraded. And so I want to just give you an example of the use of the continuum theory protocol in the context of this precise question of diffusion and reaction, which again goes under the title of reaction diffusion. So there are many aspects of this that are identical to the continuum protocol writ large. So first of all, we identify the field variables, which in our case is going to be the concentration of bicoid. So I'm going to refer to bicoid as BCD. And the concentration as a function of position is our relevant field variable. Note that I have schematized this as a one-dimensional problem. I'm not saying that the embryo is one-dimensional. I'm saying that there's only one coordinate that shows up in the concentration. Even though it lives in 3 dimensions, the x-coordinate, according to this version of the model, is the only relevant variable. The conservation law, imposed conservation laws, that's the second point. It's a little bit different than we've done before because it's saying that in a time interval delta t, the change in the number of molecules in our little box is given by the stuff that flows in minus the stuff that flows out minus the stuff that decays. So this is protein degradation, which occurs with some rate constant r, and what we're trying to do is we're trying to account for all of these features. So the change in n is given by those pieces. Next is infer or guess or measure the constitutive law, and here we're going to exploit, as we have already done, we're going to exploit Fick's law. So Fick's law is basically telling us that there's a diffusive flux. It's a phenomenological model, and I'm going to come back to phenomenology in a later philosophical interlude. And the idea has already been explored several times. Just recall that the units of flux are number of molecules per area per time, which explains why over here we have the area, the cross-sectional area of this face up here. So that is the area A, right here. Okay? So then, as usual, we derive the governing field equation, and the way we do that is by combining mass conservation and the constitutive model. And the consequence of that is that we get a beautiful equation, which is a so-called reaction-diffusion equation, as I've already said. This is the diffusion term, and this is the reaction term. And what I'm going to do right now is I'm going to just try and go through these steps in a little bit more detail. But that equation is, in some ways, the simplest version of a reaction-diffusion equation, because the reaction of interest here is nothing more than existence or not. And what I mean by that is, you could have some reaction in which two different chemical species come together and make a third species. Even a ligand-receptor interaction is of that variety. This is kind of a very sterile version, but potent at the same time, in the sense that all that happens is a given protein molecule goes away. So let's try to review the facts here. So first thing I want to say is that the change in the number is going to be equal to the number coming in from the left times the area of that face times delta t. So this is the number coming in on the left face. So maybe I'll write that. And then I subtract from that those going out on the right-hand side. So that's at x plus delta x over 2, delta y, delta z, delta t. And then I subtract off the rate constant. This is the probability of a given molecule decaying times n of x and t. So this can all be simplified. I can rewrite this as dn dt, which is the same as dc by dt, delta x, delta y, delta z. Then I can reorganize a la my usual comments about the Michelangelo statues, where this thing wants to be a derivative, and so we're going to let it become a derivative. So this ends up being delta x, delta y, delta z. And then finally minus r times c times delta x, delta y, delta z. And in the limit, as delta x, etc., goes to 0, this thing becomes dc by dt is equal to minus divergence of flux minus rc. So that's our conservation equation. This is accounting. What we've done is we've accounted. And in fact, it's conservation of mass, but in fact, mass is not conserved because of the r term. So some of the molecules go away. They go away at a rate r. And the final step is use that j is equal to minus d dc by dx. And if we plug that in here, this leads us to, in the end, the reaction-diffusion equation, which is this equation. So there you go. That's our big result. That's our reaction-diffusion equation. Great. So that's the governing equation according to our pathetic thinking in this particular case. That is the governing equation for the concentration profile. So now to go back to the actual Bicoid gradient story, what I'm going to do is I'm going to say that I will think about using this equation for the case where I have some embryo and this thing runs from 0 to L. I idealize it as a one-dimensional embryo. And what I want to do is I want to say that J at 0 is equal to some J0. This is the rate of production of Bicoid at the anterior end. So what I'm saying is that all the action from the mother it takes place in the form of the deposited mRNA, and what this tells us is that there's a certain amount of Bicoid molecules that are synthesized per unit time. And so if I wanted to find the number, the rate at which molecules are injected, so this is at x equals 0, so this, I'm calling this the number of Bicoids injected per second at the anterior end. That's going to be given by J0, which is times some effective area. And the reason I'm being a little bit cagey about that is that, the embryo is not exactly, you could think of it as like a football shaped, and so this effective area is a little bit tricky, and I'm not gonna belabor that. The other thing that I can say is that J at L is equal to 0. In other words, no material should be flowing out from the right-hand side. So I have mixed boundary conditions. On the left side, I provide a flux boundary condition where I'm saying that I want stuff to be coming in from the left, but on the right-hand side, there's no molecules exiting. And so those are the boundary conditions. And what I want you to do is we're going to consider the steady state, but, C. Crick, C. Nama Barkai, who's done really interesting stuff about this. When I say C. Crick, I just remind you, I showed you this in the previous vignette, the time needed to set up a gradient. So, I'm going to pretend that it has enough time to reach steady state, but openly acknowledging that maybe I'm missing something. So in steady state, recall our governing equation is dc by dt is equal to d squared c by dx squared minus rc, and this is going to be equal to 0. So basically in steady state, I'm throwing this out, and what you see is that means that I have an ordinary differential equation of the form shown here. Let's explore the units of d over r. So note, the units of d over r is L squared over time divided by 1 over time, which is equal to L squared. So basically what I learn is that there's a characteristic length scale, which I'm going to call lambda, which is given by square root of d over r. Or sometimes I will prefer to write it as d times tau, where tau is, if you like, the half-life of a protein. I'm being a little bit sloppy here intentionally. I'm not gonna worry about things like factors of log 2s. I'm just trying to get the essence of what's going on. So, so what I can tell you is that we can solve this differential equation. Why do I say that? Note, it is second order, it's linear, it's got constant coefficients. So I already know that the solution is of the form c of x is equal to e, let me write it as a e to the x over lambda plus b e to the minus x over lambda, where, as we already said, lambda is equal to root d tau or root d over r. Let's verify that. So dc by dx is going to be a over lambda times e to the x over lambda, and d squared c by dx squared is going to be equal to a over lambda squared e to the x over lambda. Let's plug that back into the equation. So so I have d squared c by dx squared minus, or is equal to r over d, or maybe I should write that instead as 1 over lambda squared times c. So on the left-hand side, I have a over lambda squared, e to the x over lambda. On the right-hand side, I have 1 over lambda, a e to the x over lambda. And so it checks out. So these exponentials solve this thing, and there's a technical point, which is very fun, and I absolutely think that you should do it. But I'm going to say that c of x is approximately equal to, maybe I'll write it this way, it's approximately equal to bicoid 0 e to the minus x over lambda. Why do I write that? Because I'm throwing out the e to the plus x over lambda solution on the grounds that it is it's weak in comparison with this decaying exponential term. In other words, it basically doesn't contribute. When you apply the boundary conditions, you will find that it results in a term which is less important than this one. So what we're going to do is we're going to say that the bicoid gradient is described by this simple exponential. So what have we accomplished? What we've accomplished is that I've given you a derivation of the reaction-diffusion equation, which we did right here, using the continuum theory protocol. And that culminated, indeed, in this reaction-diffusion equation. And then what we've done is we've taken that equation and we've solved it. And what we found is that we expect an exponential profile, bicoid of x is equal to bicoid at 0, e to the minus x over lambda, where, and this is big stuff, where lambda is equal to d over r. Let's just check that out. So lambda is equal to square root of d tau. If I take d to be of order, let's say 10 microns squared per second, and I take tau to be on the order of, let's call it something like few times 10 to the 3 seconds, then this gives me square root of few and then times 100, and that's in microns. So some square root of 3 times 100. Note that this length is 500 microns. And so the decay length that we get just by reasoning out, this is a typical protein diffusion coefficient. And this thing is a typical protein lifetime for case of interest here, which was actually measured. So I just plug in some numbers, and what I get is a number of order, let's say something like 150 microns, which is going to be, some characteristic scale, like a length scale over here somewhere. So this thing is an exponential, and the analysis that we did in terms of what the length scale is actually quite sensible. Okay, so that more or less summarizes what I wanted to get across in this little vignette, which is the idea of the reaction-diffusion equation, the use of the reaction-diffusion equation to solve for the morphogen profile, which we've now done. The morphogen profile is exponential, as we see, and even by plugging in some numbers, we find that the length scale of that morphogen is quite consistent with what is measured experimentally, although there's very deep questions about how that would work in a different species of fly, which I'm going to leave aside, but I really recommend a beautiful series of papers, one in particular in PNAS by Thomas Greger, Bill Bialek, and Eric Wieschaus, and maybe David Tank. Really super interesting stuff. Okay, that's all I've got on this part.